Fibrillation is a chaotic pattern of heart activity that is ineffective at pumping blood and is therefore life-threatening. A device known as a defibrillator is used to shock the heart back to a normal beat pattern. The defibrillator discharges a capacitor through paddles on the skin so that some of the charge flows through the heart. If an 11.0 microfarad capacitor is charged to 6.00 kilovolts and then discharged through the paddles into the patient's body, how much energy is stored in the capacitor? And how much charge flows through the patient's body if the capacitor discharges completely? Well, for this problem, you've probably seen this on television where they have a patient and the patient goes through cardiac arrest. So they're having a heart attack, not having a good day. And the paramedics show up and they pull out these big paddles, and at least in the shows I watch, the paramedics usually call out clear, and then when they call out clear, they send an electrical shock that passes right through the heart, hopefully to stimulate the heart back into a regular beating pattern so that the patient can be alive and well and happy, albeit with a heart condition now. Well, so this is actually a practical example. They base that on some science. The defibrillator paddles are actually a capacitor that store a lot of charge so they could send a lot of charge through the heart at one time to stimulate a regular beating pattern. So our example is working with that idea. Let's start by drawing an image of the patient's heart. Here is the heart in cardiac arrest. I'll represent the defibrillator paddles as a parallel plate capacitor. And these plates are placed on either side of the heart. We're told that the plates are charged to a certain potential difference. So I'll indicate a battery. And remember, batteries are indicated with unequal parallel lines. So this battery must provide the potential difference to the capacitor. And we're given that the potential difference of the capacitor, or at least the capacitor, will be charged to 6.00 kilovolts. We're also told the value of the capacitance of the capacitor. Now remember, capacitor has the ability to store electrical potential energy, and capacitance is a measure of that. So we're told that the capacitance of this capacitor is 11.0 microfarads. The capacitor is then fully charged, so I'll indicate the amount of charge Q. And remember that Q, the charge, will deposit on each plate of the capacitor. On the plate that's attached to the positive terminal of the capacitor, we'll have a positive Q in charge. So in other words, it will have positive charge distributed on the positive plate. Now the opposite plate, the one that's attached to the negative terminal of the battery, will have negative charge, an equal amount of negative charge distributed on that negative terminal. So this capacitor is charged by that potential difference to a total magnitude of charge of Q. And then at some point when the capacitor is fully charged, the paramedic calls clear and discharges the capacitor, allowing charge to flow to help stimulate the heart. Our goal in part A is to find how much energy was stored by the capacitor. To determine that, we could use the expression that we've previously shown for the potential energy of a capacitor, that the potential energy is equal to 1/2 of the product of the capacitor's capacitance and the potential difference across the plates of a charged capacitor. So this is pretty simple. All we have to do is plug in the values. So we have 1/2 times 11.0 microfarads. And this is multiplied to 6.00 kilovolts squared. When I plug this into my calculator, I get 198 farads volts squared. But is a farad volt squared equivalent to a joule? And we're looking for joules because we're looking for energy. So let's do a quick unit check to make sure our units check out. So I'm going to do a unit check by looking at the units of the farad and the units of the volt. A farad is the unit of capacitance. And remember, capacitance is defined as charge per unit volt. So if the units of the capacitance is the farad, then a farad is equivalent to a coulomb per volt. Well, let's put this in. Let's see. We have the units for farad volt squared must be equal to a coulomb per volt times volt squared, which is equal to the coulomb volt. Okay, so we now know that the unit of farad volt squared is a coulomb volt. Well, let's take this one step further. A volt, remember, is a joule per coulomb. And we see that the unit of farad volt squared is equal to the unit of energy, the joule. So then we could write that the potential energy stored by the defibrillator is equal to 198 joules. Part B asks us to find the total amount of charge discharged through the patient's heart, assuming that the capacitor was fully charged. Well, I know that charge is equivalent to the potential difference of the capacitor times the capacitance of the capacitor. This just comes from that little mnemonic that I like to use to remember this relationship. Valley College is quaint. Potential difference times capacitance is equal to charge. So again, this is just another simple substitution. For the potential difference, we have 6.00 kilovolts. For the capacitance, we have 11.0 microfarads. And when we plug this into our calculator, we get 6.60 times 10 to the minus 2 farad volts. Okay, and we're looking for charge. We know the units of charge is the coulomb. Let's see if a farad volt is equivalent to a coulomb. So remember, the unit of the farad, as we've shown previously, is equal to coulomb per volt. So this means that a farad volt has units of a coulomb per volt times volt, which ends up being the unit of the coulomb. And yes, that's what we're looking for. So the units of this problem check. This means that the charge that was discharged through the patient's heart is equal to 6.60 times 10 to the minus 2 coulombs.